ever stop to wonder how things, well, begin? I mean, how a cloud just appears in the sky, or how a single snowflake forms, or how a solid chunk of metal is born from a pool of molten liquid. It all comes down to a process called nucleation. So let's dive into the secret start of pretty much everything.
On the surface, it seems simple enough, right? You just cool a liquid down and it freezes. But if we zoom way, way in, down to the level of individual atoms, how does that very first tiny solid crystal manage to pop into existence out of a chaotic sea of liquid?
You'd think it would be an easy downhill slide into a solid state, but it's the total opposite. For that first little nucleus just coming into being is an incredible struggle against the fundamental laws of physics. It is literally fighting for its life from the very first moment.
To really get why this is such a struggle, we've got to talk about energy. Because in the world of physics, it always comes down to energy. Okay, so here's the deal. It's this constant push and pull, a fundamental trade-off. On one hand, there's a huge energy payoff. The atoms want to snap into that tidy, stable, low-energy crystal structure. That's the driving force. But on the other hand, there's a massive energy bill to pay. Every time you form a new particle, you have to create a surface, an interface between the new solid and the surrounding liquid. And creating surfaces costs a lot of energy.
This from-scratch method has a name: homogeneous nucleation. You should think of it as the absolute hardest way to start anything. It's totally pure, completely spontaneous, and it relies on nothing more than the random jiggling of atoms to get the job done. And this process is just incredibly risky. You've got these little clumps of atoms, called embryos, constantly winking into existence and then, poof, dissolving right back into the liquid. For most of them, the energy cost of their surface is just way too high. To survive, an embryo has to get lucky. It has to randomly grow to a critical size, the tipping point where the energy payoff of its volume finally beats the energy cost of its surface. It has to struggle up and over this massive energy hill just to have a chance to exist.
So, just how hard do you have to push the system to make this happen? Well, the theory says you need to supercool a liquid by about 20% of its melting temperature, or TM as scientists call it. And let me tell you, that is a huge amount of supercooling.
To put that in perspective, just think about molten iron. It freezes at around 1538 degrees Celsius. To get this from scratch nucleation to happen, you'd have to cool that liquid iron all the way down to about 1180 degrees, a full 360 degrees below its freezing point, and still have it be a liquid. That's just wild. Which, of course, brings up a really obvious question. I mean, the water in my ice tray freezes at 0 degrees Celsius, not -40, and molten metals solidify after just a few degrees of cooling, not hundreds. So if starting from scratch is this impossibly hard, how does anything in the real world ever manage to freeze? Well, the answer is pretty simple. Nature almost never starts from scratch. It cheats. It finds a shortcut. And that shortcut is called heterogeneous nucleation. Instead of trying to form a brand new crystal out in the middle of a perfectly uniform liquid, the crystal just forms on something that's already there, a tiny speck of dust, an impurity, or even the wall of the container. These spots give the new crystal a pre-made foundation to build on, which massively lowers that energy cost we were just talking about. And the difference between these two paths is it's not even close. The hard way, starting from scratch, needs hundreds of degrees of supercooling. The easy way, using a shortcut, can happen with less than a single degree of supercooling. So of course, nature, being efficient, is always going to take the easy route. And here's the thing. The real world is just littered with these shortcuts. Inside materials, you've got grain boundaries, tiny impurities, little defects called dislocations, and yeah, even the walls of the container holding the whole thing. They are all perfect, low-energy launch pads for a new phase to form. Now, this is more than just a cool piece of trivia about nature. It's actually one of the most powerful tools material scientists have. I mean, if nature uses shortcuts, what's stopping us from designing our own? And that is exactly what we do. By controlling where and how often nucleation gets to happen, we can basically dictate the final structure of a material. And when you control the structure, you control its properties, like its strength and toughness. We literally get to engineer the perfect start. Let's look at welding, for example. In a normal stainless steel weld, crystals start growing from the cooler edges and just march inwards. This creates these long, column-like crystals that are all lined up. And that's not great. It makes the weld weaker in certain directions and even harder to inspect for flaws. But now, watch what happens. If we inoculate the molten weld, basically just sprinkle in some tiny particles of tantalum nitride, everything changes. These particles act as thousands of pre-made shortcuts. Nucleation kicks off everywhere at once, creating a beautiful structure of small, uniform, randomly oriented grains. The result? A much, much stronger and more reliable weld.
And this trick isn't just for welding. The exact same idea is used to create incredibly tough, high-speed steels. You know, the kind used for industrial cutting tools that have to survive insane amounts of heat and wear. See, the ordinary structure, it's fine, it's okay. But for really demanding jobs, okay just doesn't cut it.
But once again, by adding our own engineered shortcuts, this time it's tungsten carbide particles, we can force the steel to form a much finer, tougher crystal structure right from the get-go. This is how you build superior performance into a material right from the most fundamental level.
All right, so let's zoom back out. After this whole journey into the secret start of things, what's the big picture? What's the main takeaway? It really boils down to 4 simple things. 1, making something new always has an energy cost. 2, because of that cost, starting from absolute scratch is just ridiculously hard. 3, nature is smart, not lazy. It always finds the lowest energy shortcut available. And 4, the coolest part? We can hijack that principle, design our own shortcuts, and build the amazing materials that make up our modern world.
And that leaves us with one last thing to think about. This principle of finding the lowest energy path, of using a pre-existing seed to get something new started, it goes way beyond just material science. You can see it in innovation, in business, even in how we learn. So the real question is, if nature always takes the easiest path to creation, what powerful shortcuts are we missing in our own lives?